Well, aren't you guys good looking today? Hey, we're gonna back it down a little bit. We've been getting into some pretty complicated looking exponents, some ugly stuff. We're gonna we're gonna tie it all into something you're probably a little more familiar with today. We're gonna see how what scientific notation has to do with exponents. But again, as always, I know, man, broken record, like your mom yelling at you, clean your room, maybe. Hey, learning. It's a very active and it requires active engagement. It's not a passive activity. Watching videos is very passive. Sleeping's more passive. It's really about it. So if you want to learn from this, if you want to use the time well, you have to pause the video, try problems, write down questions. When you answer questions, you unpause the video, go back, write your answers, all that kind of stuff, right? Come on, bro. Come on, bro, potato chip. All right, let's get to it. Here we go. We're going to be talking about scientific notation and what they have to do with exponents, positive and negative. So check this out. Now, of course, scientific notation is a single digit, like 5, followed by a decimal, and then some decimal expansion. It might be 0 to something like that, 5.02 times, and then it's a power of 10, so 10 to some power, you see? And so if the 10 has a positive exponent, like 21, that's a huge number. 21 zeros. It's a huge, gigantic number. One that would take forever to write out, wouldn't make any sense, right? Or 5.02 times 10 to the power of negative 21 is a very small number. It's a tiny, tiny, tiny number because this is division. So this is 5 times a giant number. This is 5, basically, 0.02, divided by a giant number. When you divide by a giant number, man, it gets really small. Um, like 1 in a million. 1 in a million is a very, very small percentage. This is way smaller. A million is 10 to the 6. This is way smaller than that. Do you see? Now, the reason we use scientific notation is it gives us an easy way to write some very long numbers. They could be really big numbers, really small numbers, but for writing them out, it takes a lot of space. So that's why we use this, right? Now, the reason this has to do with exponents is we actually use exponents. We use powers of 10 to write these types of numbers. So, for example, let's say we had 3.04 times 10 to the third. And let's say we were going to add that to 2.7 times 10 to the third. Check this out without a calculator. You see how they're both 10 to the third? That means we could add those coefficients. That would give us 5.74 times 10 to the third. That's what that would equal. Do you see how that works? Because they are exactly the same. Exactly the same unit. These are the coefficients. This is like saying, what is 3.04x plus 2.7x? Well, that would be 5.74x. Do you see? Exactly the same. These are the coefficients. They're multiplying. We write it out a little different here with scientific notation, but it's the same thing. All right. Same thing would work with subtraction. Same exact thing would work with subtraction. But, yeah, so if you did subtraction, you just have to subtract those two. You're going to get like point whatever, right? In fact, let's do that. Let's do that. Let's do 3.04 times 10 to the third minus 2.7 times 10 to the third. Well, check this out. This is going to be something times 10 to the third. Now, this is going to be a positive number because, 3.04 minus 2.7, right? So 4, 0.34. So this would be 0.34 times 10 to the third. Now the problem with that is, of course, that's not scientific notation. So to make this scientific notation, check this out. A lot of times they say, oh, you move it to the left, you have to add, or move it to the right, you subtract, whatever. But check this out. If I take 0.34 and I change it to 3.4, isn't that going up? Isn't that the larger number? So that means I have to make this a smaller number. 3.4 times 10 squared. So I made this one larger, so I have to make the other one smaller so that they're still equal. These two things are exactly the same. This is 340. This is 340. They're both 340. This one's in scientific notation. This one's not. So when you make this larger, when you make this number larger, you have to make this one smaller. The other would work exactly the same way. Like if you had, say, 551.2 times 10 to the 14th, for example. That's not scientific notation. 5.12 times. So see, I made this smaller. It means I have to make that bigger. Those are exactly the same number. Yeah. Okay. Now, what about multiplication? So let's say we had 1.4 times 10 to the third, and let's say without a calculator, 2.1 times 10 to the negative fourth. Ooh, whoa. What's going to happen here? This is funky, right? Um, we're going to multiply these whole numbers, and we're going to multiply these together. It's all multiplication. You see, this is a number times another number times another number times another number. This is like 2 times 3 times 4 times 5. That'd be the same as 2 times 4 times 3 times 5, right? Excuse me. That's what we're doing. We're going to multiply these parts together. We're going to multiply the exponent parts together. So, first of all, when I multiply the exponent parts together, what's this equal? Doesn't that equal 10 to the negative 1? This is the same as 1/10, so this is going to be a decimal, smaller than 1. So, times 10 to the negative 1 from these two. And then, I don't know what 1.4 times 2.1 is. Let's do it. So 2.94. 2.94. 2.9. No, 29. No, it was 2.94. Math is hard, bruh. To the negative 1. The reason it's right, because we're multiplying. So then 2 decimal places. Yeah, so 2 decimal places. I did it. I got confused with adding right there. So anyway, 2.94 times 10 to the negative 1. Boom, boom, done. Dang, bro. You know what's kind of weird? And I noticed this. I've seen this happen. I've noticed it with myself. I've also noticed it with other math teachers. And I've also especially noticed it with lots of students in school. Um, Sometimes the basics we have to go back and really think because man, it's so easy to get confused. So you just got to be careful. Just take your time with stuff like that. Yeah, it makes you feel dumb. You just forgot. You haven't done it for a while. So that's why I'm going to leave this in here because it does happen to everybody. It's really easy to happen, especially if you're kind of distracted. So anyway, here's what we've got. Right? With scientific notation, we're dealing with exponents, and we're just going to be applying the same rules we already know about exponents to these kinds of problems. And then in our final answer, we have to just make sure that our answer is in scientific notation. So that's a full number followed by a decimal, then the expansion of the decimal times a power of 10. So that's the trick right there, is making sure this is a one-digit number. Now, what if, without a calculator, let's say we had 3.2 times 10 to the third plus 4.1 times 10 to the fourth. And we wanted to add those together. In fact, let's say this was giant exponents. So you're not going to be able to write that out, right? Um, Hold on. There we go. Let's say 32. I'm going to write it again to make it pretty. Let's say 3.2 times 10 to the power of 31 plus 4.1 times 10 to the power of 32. So big old giant numbers we're never going to add together by writing them out. And let's say we cannot use a calculator. Let's use what we know about scientific notation and exponents and see if we can get these. Now, first of all, these are not like terms. This is 10 to the 31. That's 10 to the 32. They're not the same. That's like trying to add these two together. You can't. That's 3 x's. That would be x plus x plus x. And that's 5x squared. So that would be 5 of them. Well, you get the idea, right? I'll go ahead and write them. Well, almost ran out of room. Do you see? They're not like terms. You can't add them together. Same thing here. This is 3.2 of those, and this is 4.1 of something else. But what we can do is we can make these the same. I can either turn this into a 32 by adjusting this, or I can make this into a 31 by adjusting this. It doesn't really matter. Now I'm going to do, let's change this one. Let's make that into a 31. So this is 3.2 times 10 to the power of 31. And then, now, if I make this times 10 to the 31, didn't I make that smaller? So that means I have to make this bigger. Those two numbers are equal. 4.1 times 10 to the 32 is the same as 41 times 10 to the 31. These are the same, do you see? And I made them the same so that now I have like terms. So this is going to be 44.2 times 10 to the power of 31. Now the problem is that's not scientific notation. 4.42. Now this is a smaller number, which means to keep it balanced, I make that a bigger number. Do you see? just got to keep it the same. Got to keep it equal. Got to balance it out. Boom, you're done. Anyway, that's how scientific notation is that's how scientific notation makes use of exponents. And so if the bases are the same, you can add. If you're multiplying, you add those exponents. Negative exponents, we leave them written as negatives. We don't actually write them as a fraction, but that's why negative exponents in scientific notation, we leave them there, but that means a really small number because you have a small number, that decimal, divided by that power of 10, which is, usually in the millions. Anyway, oh yeah, you guys are good looking too today. Man, don't forget.